Okay, so let's take a look at a problem that's going to combine everything we've done so far. The first, I've already gone to the table of light nuclides and recorded that sodium 24 decays by beta and has a half-life of 15 hours. So when I get to writing the decay equation, it'll be Na24 decays by beta, which is 0, -1. Sodium is element 11, so this will form element 12, which is magnesium. Now I need to find the energy per decay, which means I need to look at the mass decrement between the sodium and the magnesium. And remember, I don't include betas. So I'm going to go back to my table of light nuclides for a quick second. And I get that the sodium has a mass of 23.990962, whereas the magnesium nuclide has a mass of 23.985042. So I'm going to subtract these two values to get my mass decrement. 23.9900962 minus 23.985042 gives me a change in mass equal to 0.000, nope, only two zeros, 505 atomic mass units. Now to convert it to energy, I need to multiply by 931, and this will give me the energy per decay in AMU. Sorry, the energy per decay in MeV. So 9.71 MeV. Next, we want to know what mass of sodium remains after 40 hours. I need to use the information that the half-life is 15 hours. I'm going to use a time of 40. I want the amount remaining. My starting amount is 0.01 grams. So with the half-life, I'm going to get the decay constant. 15 equals ln2 over lambda. ln2, close my parentheses, divided by 15 yields 0.0462 for lambda. Now we can do n equals n naught e to the negative lambda t. N equals 0.01 e to the negative 0.0462 times the 40 hours that we allowed this to decay for. So this answer times 40, e to the negative that, times 0.01 tells me that we have remaining 0.0016 grams. The next question I'm asked is how much energy was released during 40 hours? We started with 0.01 grams. Then we lost a certain amount, and at the end we had 0.0016 grams remaining. This number here is going to tell me how many grams decayed. So 0.01 minus that tells me that 0.00842 grams of Na24 decayed. So now I can use this information to figure out how many atoms decayed. And if I know how many atoms decayed, and I know the energy per single decay, I can figure out how much total energy was released. So 0.00842, I'm going to divide by the molecular weight to get the moles. And now I'm going to multiply by Avogadro's number to get the number of atoms. So times 6.02 times 10 to the 23rd yields 2.11 times 10 to the 20th atoms decayed. with an energy of 4.1 mega electron volts per decay, gives me a total of 9.95 times 10 to the 20th MeV. However, this question asked you for the amount of energy in joules, not in MeV. So I need to convert it to joules using the conversion factor that 1 MeV is 1.6 times 10 to the negative 13th joules. So I'm going to multiply by 1.6 times 10 to the negative 13th. And that yields, I'm going to put it into scientific notation, 1.6 times 10 to the 8th joules. Okay, for the last part of the problem, what was the initial rate of decay in counts per second? I'm going to use A equals lambda times the number of atoms that I had present in the beginning. Now, we have to be careful here because this lambda needs to be calculated from the half-life in seconds. And so 15 hours times 60 minutes times 60 seconds, 15 times 3,600 yields 54,000 seconds. So T1 half equals ln2 over lambda. I'm going to plug in the 54,000. So ln2 divided by 54,000 yields 1.28 times 10 to the negative 6th seconds. Sorry, 1 over seconds. This is my decay constant. So this is the lambda. I need the number of atoms at the beginning of the problem, not the number of atoms that decayed. So the number of atoms at the beginning of the problem was 0.01 grams divided by 24, and then I'm going to multiply that by Avogadro's number. 0.01 divided by 24 times 6.02 times 10 to the 23rd yields 2.51 times 10 to the 20th atoms. Now I have lambda and I have n, so I can get the activity. By multiplying these two numbers together. And we get 3.21 times 10 to the 14th counts per second. This would be the initial rate of decay when we had the most number of atoms present, but it would slow over the course of the reaction. So you can see how in a large problem, we could be asked to put everything together. Most notably, what's most interesting to me is we can figure out over the course of time how much of something decays and therefore how much total energy is going to be released in that process.